Welcome to another many-body gravitational simulation video. This simulation scenario reveals a surprising behavior where a spherically propagating high-density wave is created and continually expands during the 20 billion year simulation run. However, it begins, as you see, with a dark matter-like halo of 20,000 particles arranged in the famous Navarro-Frank and White density profile with a scaling radius of 10 kiloparsecs. The total mass of this halo is 1 trillion solar masses, or roughly the same mass as our Milky Way galaxy. Initial velocities for the particles are created to put particles in nearly circular orbits based on the total mass inside their respective positions. Interparticle gravitational interactions are also force softened when their separation distances are under 2 kiloparsecs. The video begins with the full view of all 20,000 particles in a box 4 megaparsecs in width. The left box shows the view looking down on the XY plane from the Z-axis, and the right view is looking down on the ZY plane from the X-axis. As we move forward, an additional explanation of what you are seeing in the plot windows is warranted. Particles have color, and the different colors indicate their position out of the viewing plane. Red means towards the viewer and blue means away from the viewer. More red and more blue means nearer and farther respectively, and white indicates that the particle is very close to the viewing plane. Because the high-density wave is just beginning to be seen at this extended plot scale, let's restart time and view the simulation in a box size of 200 kiloparsecs. As we start the time going forward, the high-density shell will become visible and expand outward. There are many interesting properties of the high-density shell observed in this video. First, after about 4 to 5 billion years, the high-density shell moves outward at nearly a constant speed, which is about 13.5 kiloparsecs per billion years. Secondly, the total mass in the shell remains at about 10% of the total mass. This means that there are about 2,000 particles participating in the shell. Third, there is a secondary shell of particles that follows the primary. This secondary shell appears like a ripple wave, like one might see when a pond surface is disturbed. Let's pause time and rotate the system about the y-axis for 180 degrees and back again to show off the spherical shape of the shell. Let's zoom out to a viewport size of 700 kiloparsecs and continue to show the advancement of the wave. The most remarkable aspect of the high-density wave is that the particles participating in the high-density region are continually replaced with new particles from the radial vicinity. In other words, the particles in the shell at one point in time are not the same particles at a later time. We will revisit this later in the video. Here's a way to think about how this happens. As the traveling shell moves outward, local particles are attracted to and scatter off the high-density region. However, as the wave passes, these scattered particles return to their initial orbital neighborhood. If you are wondering about the background sounds in this video, they were created from the simulation data and are related to the particle orbital changes as the wave moves through the particle region. How does this high-density wave get started? To understand the answer, we need to zoom way into the halo interior and watch carefully what happens to the interior particles. Notice that the particles in the interior expand outwardly and then collapse under their own gravitational attraction. Let's restart this segment and watch again. Those interior particles take about 200 million years to expand and then to collapse back inward. But now look what happens. A shell of mass is created and starts moving outward, and by 400 million years clearly stands out as a region of higher density. And as we have seen, this high-density shell of mass continues to move outward for over 20 billion years. As mentioned earlier, this next sequence will offer up video evidence that the particles participating in the wave are continually changing. I will do this by restarting time from the beginning and set the box size to 800 kiloparsecs. I then will add a plot to the corner of each of the screen captures that shows the particle index number and its distance out from the center of the halo, as seen in this example. I will run this forward, but with compressed time to see the entire 20 billion years in just under 7 seconds. The particle index plots are synchronized in time with the plots in the viewports. Watch where the particles are vertically grouped. That is where the high-density shell is at that time period. Then watch over time how the particle index moves with the vertical group. That sequence is amazing. Let's let it run several more times just for fun. Note that there is evidence for at least 3 and maybe 4 secondary waves following the main wave. This combined view conclusively demonstrates that the particles in the wave change over time and that the particles return to their original orbital distances. Watching the observed particle exchange, one is reminded that Lin-Shu density wave theory for galactic spiral arms is thought to share this same property. Clearly, the triggering mechanism for creating galactic spiral arms would have to be significantly different than how the wave in this video began. Hey, if you made it this far, thanks for watching my video.